Students will be able to find domain and range from a graph, find x and y intercepts, and test for symmetry. Find the domain and range of each graph. Oh, the domain is what x values are being used to graph this function. And all the values, now think about not just going down, but the graph is certainly going down and to the left. But this arrow means that this will go down and to the left forever. So the domain for this is negative infinity, and then we'll use all the x values all the way up to 5 and including 5. Now this graph goes all the way down, so we're including the y values, negative infinity all the way up to a value of 2. On this one, we're going all the way to the left and then going to positive 3. So the domain will be negative infinity to 3. And then the range is the bottom y value that we're using is negative 2. And then this is going up and left forever. So up to infinity. On this one, the farthest left x value that we're going to but not using is negative 4. So we have negative 4, and then we're using all the x values up to 3. And we're actually using 3. The range is down here at negative 5, and the highest y value is going to be 2. Use the graph of each function to find its y-intercept and zeros, in other words the x-intercepts. Then find these values algebraically. I'm not exactly sure what the y value, the y-intercept is, but it looks like the zero is 1, 2, 3. So how should we write this? And find, use the graph. So zeros are x equals 3. Let's get the y-intercept. Now the y-intercept will be where x is 0. So f of x is equal to 0 squared minus 6 times 0 plus 9, so the y-intercept is 9. Y-intercept is the point 0, 9. Now what we could do is we plug, to find the zeros, we plug in 0 for y really. So let me show that. 0 equals x squared minus 6x plus 9. Now we're kind of doing this, algebraically now. 0 equals x minus 3. So the only 0 is 3, but it counts twice. So there's that 0 of x equals 3. Use a graph of each equation to test for symmetry with respect to the x-axis, y-axis, and the origin. Support the answer numerically, then confirm it algebraically. Well, we'll just show here that this is an odd function because it's symmetric over the origin. If there's a point here, there's a corresponding point across the origin. Now let's confirm this algebraically. And to confirm that we have an odd function, f of negative x has to equal negative f of x. That's how you confirm algebraically. So here's the function right here. So f of x, f of negative x, is really, if we wrote it all out, is negative 10 over negative x. And the opposite of f of x is 10 over x. Well, negative over negative is positive. So 10 over x is equal to 10 over x. And we've shown that this is actually an odd function, which means it's symmetric over the origin. Symmetric over the origin. Determine whether a relation represents y as a function of x. Write either function or not a function. Well, to be a function, it has to pass the vertical line test. In other words, 1x has to give you one and only one y. Well, here we're getting 2 y's out of an x value, so this is not a function. When we have an equation, we need odd powers of y. Y is to the first power, so when we solve for y, we won't have that plus or minus. So this is, yes, this is a function. Find each function value. So find f of negative 2. F of negative 2 is equal to the square root of 4 minus 3 square root of 1, 1. f of a plus 2, f of a plus 2 is going to be equal to square root of a plus 2 squared minus 3. Now we got to FOIL this. So square root of a squared plus 4a plus 4, then minus 3. So we have the square root of a squared plus 4a plus 1. State the domain of each function using interval notation. Now there's only two problems with domain: even radicals and denominators. And here we have an even radical. Now negative x plus 1 has to be greater than 0. So negative x has to be greater than negative 1. X has to be less than 1. Remember, when we divide by negative, we have to switch the signs around. Now we're going to use interval notation to answer this. So x has to be less than 1. Negative infinity to 1, but don't include 1. Over here we have a denominator, x plus 3, x plus 1, and so x cannot be negative 3. That would make the denominator 0, and x cannot be negative 1. So now the domain, we just have to skip over negative 3 and skip over negative 1. So negative infinity to negative 3 to negative 1, and then negative 1 to infinity.